Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. So today I will continue my lecture on advanced thermodynamics MME6154 for chapter 6, second law of thermodynamics. In chapter 6, we will learn on the introduction of the second law of thermodynamics, and we will identify valid processes as those that satisfies both the first and second laws of thermodynamics. We will learn or discuss the thermal energy reservoirs, reversible and irreversible processes, heat engines, refrigerators, and heat pumps. I will also describe the Kelvin, Planck, and Clausius statements of the second law of thermodynamics. And then I will describe the Carnot cycle and examine the Carnot principles, idealized Carnot heat engines, refrigerators, and heat pumps. In previous chapters 3, 4, and 5, first law of thermodynamics, where conservation of energy principle is applied to processes involving closed and open system. As pointed out repeatedly, energy is a conserved property and no process is known to have taken place in violation of the first law of thermodynamics, where a process must satisfy the first law to occur. However, satisfying the first law alone does not ensure the process will actually take place. That is why we will learn in this chapter about the second law of thermodynamics. Let's see this situation. We have a situation 1, a cup of hot coffee left in a cooler room. So what will happen? So normally, you guys can predict what will happen. The coffee will eventually cools off. This process actually satisfies the first law of thermodynamics, since the amount of energy lost by the coffee is equal to the amount of heat gained by the surrounding air. We remember about the energy balance equation for first law of thermodynamics, where the energy is conserved. E in minus E out equal to delta E. Now let's see situation 2. A cup of hot coffee left in a cooler room. What will happen? For reverse process, the hot coffee getting even hotter in a cooler room. This process will never take place. Yet, doing so will not violate the first law. As long as the amount of energy lost by the air is equal to the amount gained by the coffee. As you guys can see, situation 1 and situation 2 is the same. However, what happened to situation 1 and situation 2 is different. First, in situation 1, the coffee will eventually cool off. So it satisfy the first law of thermodynamics, where the amount of energy gained and loss is the same. However, in situation 2, it is a reverse process, where the hot coffee getting even hotter in a cooler room. In this situation 2, the total amount of energy is still the same. However, it will never take place. It is not violating the first law. However, it will never take place. Let's see. For situation 1, a cup of hot coffee does not get hotter in a cooler room. Situation 2, transferring heat to a wire will not generate electricity. These processes cannot occur even though they are not in violation of the first law. So processes must be conducted in one way, where processes occur in a certain direction and not in the reverse direction. So as I already mentioned before, even though in these two situations it doesn't violate the first law of thermodynamics, however, situation 2 will never happen because of the direction. These processes cannot occur even though they are not in violation of the first law, because processes occur in a certain direction and not in the reverse direction. For example, if you touch something that is hot, you will feel burned. You will not feel cold. So that is already confirmed, okay, in this world. Okay, it is like sunnatullah. It is happen like that. Okay, it cannot become reverse. Okay, so in this chapter we will learn about the second law and how this processes is complete, okay, by satisfying both first and second law. Okay, it's already written here. A process must satisfy both the first and second laws of thermodynamics to proceed. So let's see the major use of the second law. The second law may be used to identify the direction of processes. The second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and the transformation of energy from one form to another. Okay, first law of thermodynamics, with no regards to its quality. However, in the second law, it provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. The second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems such as heat engines and refrigerators, as well as predicting the degree of completion of chemical reaction. Now, we have learned about the definition of second law of thermodynamics. So now in subtopic 6.2, I will explain about the thermal energy reservoirs. Okay, what is thermal energy reservoirs? I believe most of you already understand what is reservoirs are. Okay, a hypothetical body with a relatively large thermal energy capacity. Okay, so how to calculate thermal energy capacity? Mass times with specific heat that can supply or absorb finite amounts of heat without undergoing any change in temperature is called a thermal energy reservoir or just a reservoir. In practice, large bodies of water such as oceans, lakes, rivers, as well as the atmospheric air can be modeled accurately as thermal energy reservoirs because of their large thermal energy storage capabilities or thermal masses. Okay, so you understand thermal energy reservoirs means that they can supply or they can absorb a finite amounts of heat, okay, finite, okay, without undergoing any change in temperature. For example, okay, for example, you pour one full of hot water in a sea, okay, in an ocean, okay, at the beach, okay, you just pour one whole of kettle of hot water to the sea. So will the sea change temperature? No, they will not change temperature even though you absorb, even though the sea absorb the amounts of heat from the hot water. Okay, so that means by the thermal energy reservoirs. Okay, so example, the atmosphere does not warm up as a result of heat losses from residential buildings during winter. So this is another very good example. Okay, during winter, lots of houses will use uh, heat, okay, uh, to heat their houses. So even though this heat loss will go to the atmosphere, it will not warm up the entire atmosphere. Okay, so that is the meaning of the thermal energy reservoirs. Another example, megajoules of waste energy dumped into large rivers by power plants do not cause any significant change in water temperature. Two-phase system can also be modeled as a reservoir since it can absorb and release large quantities of heat while remaining at constant temperature. A body does not have to be large in size to be considered a reservoir. Okay, means that any physical body whose thermal energy capacity is large relative to the amount of energy it supplies or absorbs can be the reservoir. A reservoir that supplies energy in the form of heat is called source, and the one that absorbs energy in the form of heat is called a sink. So thermal energy reservoirs also called heat reservoirs. So we have source and also sink. So thermal energy source will supply heat. Thermal energy sink will absorb heat. But both of these is thermal energy reservoirs. Okay. Now I will show you one video on the definition of second law and also some related information on the heat engine. So you guys can see from this video.
Heat engines and second law of thermodynamics. According to the first law of thermodynamics, heat and work are mutually interchangeable. This law does not mention about the direction flow of heat. Second law of thermodynamics gives the direction of flow of heat energy. Before stating the law, let us see how heat energy is converted into mechanical energy in a heat engine. Heat engine is a device used for converting heat energy constantly into mechanical work. The schematic diagram of a heat engine is shown here. The three essential parts of a heat engine are source or hot body, working substance, and sink or cold body. The working substance is taken along a cycle of operations. In this process, the working substance absorbs heat from the source, transforms part of it into mechanical energy, and the remaining part of heat is rejected to the sink. After completing the operation, the working substance comes back to its original state. Heat energy is never converted completely into mechanical energy. That is, efficiency of a heat engine is never equal to 100%. Thus, we can define efficiency of an engine as the ratio of external work done to the amount of heat absorbed from the source. In heat engines, the working substance takes heat Q1 from source at temperature T1, rejects the heat Q2 to the sink at temperature T2, and does some work W. Eta is equal to Q1 minus Q2 by Q1. Eta is equal to 1 minus Q2 by Q1. There are two types of heat engines. They are internal combustion engine and external combustion engine. Petrol and diesel engines are internal combustion engines. Steam engine is an external combustion engine. Click on the link provided to see the working of an internal combustion engine.
Okay, here you can see the process of an internal combustion engine. From intake stroke to compression stroke, and then power stroke, and then exhaust stroke.
The fact that heat energy is never completely converted to mechanical energy has become the second law of thermodynamics. There are several equivalent statements of the second law of thermodynamics. Lord Kelvin stated, "It is impossible to construct a device operating in a cycle for the sole purpose of extracting heat from a reservoir and changing it entirely into an equal amount of work without rejecting a part of the heat." This statement simply means an engine can convert only a part of the heat energy into mechanical work. Clausius statement: "It is not possible for a self-acting machine, unaided by any external agency, to transfer heat from a body at low temperature to another body at higher temperature." This statement also means no heat engine is 100% efficient.
Okay, so you have learned previously about the definition of second law, and then you learn about the thermal energy reservoir, where we have the source, where the source supply heat to the mechanical work, and then we have also the thermal energy sink that absorb the heat, and then from this video we can understand that heat engine, heat engine uh, uh, associated with this thermal energy reservoirs. Okay, we have a source that supply heat Q1, to this device, and then it will release some heat Q2, and it will be absorbed in sink, thermal energy reservoir sink. Okay, and it is also stated that in heat engine the total efficiency is not 100%. It's not totally 100% because we have work here. Okay, work equal to Q1 minus Q2. Okay, what is supplied by source will never become 100% because there is Q2 released from this device. Okay, so that is what the videos said just now. Okay, so now we will continue on the 6.3 subtopics heat engine. Okay, in subtopic 6.3 heat engine, okay, work can easily be converted to other forms of energy, but converting to other forms is not easy. The mechanical work done by the mechanical shaft is first converted to the internal energy of the water. This energy may leave the water as heat, as shown here. Any attempt to reverse this process will fail, means that transferring heat to the water does not cause the shaft to rotate. Thus, work can be converted to heat directly and completely. But converting heat to work requires a special devices called heat engine. So, in a way, heat engines is a device to convert heat to mechanical work, to work. Okay? Heat engines differ considerably to one another, but all can be categorized by the following. First, they receive heat from a high temperature source, uh, such as solar energy, oil furnace, nuclear reactor, etc. They convert part of this heat to work, usually in the form of a rotating shaft. And then they reject the remaining waste heat to a low temperature sink, which is the atmosphere or rivers or ocean, and then they operate on a cycle. Heat engines and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called the working fluid. So as I already explained before in this video, we have heat engine here. Okay, it receive the device receive a heat Q1 from source. Okay, thermal energy reservoir of source, they supply heat, and then it will release some heat, Q2, to the thermal energy reservoir sink, and from this heat it convert to the mechanical work. So this is this is the diagram of the heat engine as explained in this definition. Okay, so high temperature source, Q in, heat engine, and release Q out to low temperature sink. And then it will give W, work net out. Part of the heat received by a heat engine is converted to work, while the rest is rejected to a sink. Now, this is one example of a heat engine in a steam power plant. The work producing device that best fits the definition of a heat engine is the steam power plant. It is an external combustion engine. The combustion takes place outside the engine, and the thermal energy released during this process is transferred to the steam as heat. Okay, this is the schematic figure of a steam power plant. Okay, we have Q in, okay, from to boiler. Okay, and then it will go to turbine and release some work. Okay, at the same time, it release Q out to the condenser. Okay, and we also have pump here to make sure the steam power plant work in a cycle. Okay, so Q in, amount of heat supplied to steam in boiler from a high temperature source. In this case, it is furnace. Q out, amount of heat rejected from steam in condenser to a low temperature sink. Okay, for example, the atmosphere or river or ocean. W out is the amount of work delivered by steam as it expands in turbine. W in, amount of work required to compress water to boiler pressure. Okay, this is the example. Okay, heat engine, W out, W net out, and also W in. A portion of the work output of a heat engine is consumed internally to maintain continuous operation. So W net out equal to W out minus W in. At the same time, W net out equal to Q in minus Q out. Okay, kilojoule. The unit SI is called kilojoule. Alright. So from the equation just now, equation 6.2, W net out equal to Q in minus Q out, it represents the magnitude of the energy wasted in order to complete the cycle. Okay. So, but Q out is never zero. Okay. As you already watched the video just now, Q out will never be zero. So, Q in, okay, if this is zero, then W net out is equal to the Q in, but it is impossible. Okay, the net work output of a heat engine is always less than the amount of heat input. Only part of the heat transferred to the heat engine is converted to work. Okay, if Q out is zero, W net out will be equal to Q in, so the efficiency will be 100%, and it will never happen. Okay, the fraction of the heat input that is converted to network output is a measure of the performance of a heat engine called the thermal efficiency. So thermal efficiency will never be 100% because there will be Q out, okay, released from the heat engine. Okay, it will never be zero. Okay. Okay, so this is an example of a heat engine. Okay, we have high temperature reservoir heat engine, QH, okay, supply heat QH from high temperature reservoir to the heat engine, and from the heat engine, it give work, okay, work net out, and also it release some heat, okay, QL to the low temperature reservoir at TL. Okay, some even the most efficient heat engines reject almost one half of the energy they receive as waste heat. Okay, here we can see that heat input is 100 kilojoule, and then it release or reject waste heat almost one half of the energy that they receive. So as we can see here, waste heat is 80 kilojoule and 70 kilojoule. Okay, and we can see that the net work output is only 20 kilojoule and 30 kilojoule. So in this example, we can see that this heat engine perform better than this one. Okay, where we can see the uh, the heat supplied by the furnace is 100 megajoule, and then work net out is 55 megajoule, and it only release low heat to 45 megajoule to the atmosphere. Okay, some heat engines perform better than the others and convert more of the heat they receive to work. Alright. So, in order to know which heat engine is better than the other, we have to calculate the thermal efficiency. Okay, the eta. Okay, this is eta. Okay, the equation will be net work output divided by the total heat input, or W net out equal to Q in minus Q out, and then we can calculate eta equal to W net out over Q in. Okay, at the same time, okay, this is the same. QH is equal to Q in, QL equal to Q out. So we can derive the same equation of the thermal efficiency eta. Alright, so I already give you one example here. Heat is transferred to a heat engine from a furnace at a rate of 80 megawatt if the rate of waste heat rejection to a nearby river is 50 megawatt. Determine the net power output and the thermal efficiency for this heat engine. So you can use this equation and try to do this question by yourself. Okay, now in the video that we watched just now, it does stated the second law of thermodynamics, Kelvin Planck statement. Okay, it related to heat engine. So I just want to recap again what these statement are. Okay, so in a Kelvin Planck statement, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay, so it is impossible when you get QH, okay, QH equal to 100 kilowatt, okay, Q dot H 100 kilowatt, and then you can deliver W net out equal to 100 kilowatt. It means that there is no QL, Q dot L equal to 0. So it is impossible like this because in every heat engine, even it is most powerful heat engine, it still will release a small amount of heat, okay, to the thermal energy reservoir sink. Okay, it cannot deliver the whole 100% thermal efficiency. Okay, no heat engine can have a thermal efficiency of 100%. Or as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. The impossibility of having a 100% efficient heat engine is not due to friction or other dissipative effects. It is a limitation that applies to both the idealized and the actual heat engine. Okay, so this is the example of heat engine that violates, okay, that violates the Kelvin Planck statement of the second law. Now, refrigerators. Okay, just now we learned about heat engine. So now let's move on to the refrigerator. So energy transfer in the form of heat, higher temperature body to lower, takes place between the body and the surrounding medium until thermal equilibrium is established. So you have no heat transfer, okay, 25 degree of room air, and then time to time it becomes uh, much more cold, okay, so it becomes 5 degree Celsius. Okay, you can see the amount of heat 8 joule per second and heat 16 joule per second. So the temperature becomes smaller. Okay, is this correct? Okay, so the reverse process, the transfer of heat from a low temperature, medium to a high temperature requires one special devices, namely refrigerator. So it is a reverse process of heat engine. Okay, you can see here cold refrigerated space at TL temperature low. Okay, it supply a low amount of heat QL to the system, to the refrigerator system, and refrigerator system will release the amount of heat QH to the warm environment. Okay, and there is a work net in required input in the refrigerator. So basically, it is a totally a different a reverse process of heat engine. Okay, I think you guys already noticed that at your fridge, okay, your refrigerator, at the behind of your fridge, okay, there will be a coil. Okay, so near to this coil position, it is very warm. Okay, the atmosphere is very warm. Means that this process is happening. Okay, means the refrigerator is kept cool, but it release heat to the environment. Okay, so we can sense the heat from the coil or near to the coil. Okay. So refrigerator like heat engine are cyclic devices. Okay, the working fluid used in the refrigeration cycle is called refrigerant. The most frequently used refrigerant cycle is the vapor compression refrigeration cycle. Involve four main components: a compressor, a condenser, an expansion valve, and an evaporator. In a household refrigerator, the freezer compartment where heat is absorbed by the refrigerant serves as the evaporator. Meanwhile, the coils behind the refrigerator where heat is dissipated to the kitchen air serve as the condenser. So this is what I explained to you just now. Okay. So basic components of refrigeration cycle and typical operating conditions. So we have four components. Okay, here condenser, compressor, evaporator, and also expansion valve. Okay, which is already explained here. Alright. So in a refrigerator, let's see the first component, okay, compressor. The refrigerant enters the compressor as a vapor and is compressed to the condenser pressure. Okay, and then it moves to condenser number two. It leaves the compressor at a relatively high temperature and cools down and condenses as it flows through the coils of the condenser by rejecting heat to the surrounding medium. Okay, and then move on to the three, the expansion valve. It then enters a capillary tube where its pressure and temperature drop drastically due to the throttling effect. And then last, it moves to the evaporator. Okay, you can see a coil here. The low temperature refrigerant then enters the evaporator, where it evaporates by absorbing heat from the refrigerated space. The cycle is completed as the refrigerant leaves the evaporator and re-enters the compressor. So these are the process of a refrigerator. Okay, sometimes in the exam, you will be asked to explain, okay, how refrigerators work. Right? So you have to write like this. Alright, so recap. Last time in previous chapter, we learned about throttling valves. Okay, where throttling valves are any kind of flow restricting devices that cause a significant pressure drop in the fluid. Okay, what is the difference between a turbine and a throttling valve? Okay, because it is also a significant pressure drop. Okay, so the pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason, throttling devices are commonly used in refrigeration and also air conditioning application. Okay, so here we can see the figure 530 and 531. The temperature of an ideal gas does not change during a throttling. Okay, it doesn't change. Okay, H equal to constant and process since H is HT, so H2 equal to H1. In this figure, during a throttling process, the enthalpy, flow energy plus internal energy of a fluid remain constant, but internal and flow energies may be converted to each other. The conservation of energy equation for single stream steady flow device. So it is a flow energy PV plus with internal energy. So we can get the work U2 plus P2 V2 equal to U1 equal to plus P1 V1. Okay, this is internal energy and this is flow energy. Okay, the coefficient performance of refrigerator. The efficiency of a refrigerator is expressed in terms of the coefficient performance (COPR). Okay, remember in heat engine, the efficiency is denoted with a symbol eta, TH. But in refrigerator, the efficiency, okay, the coefficient of performance is denoted with a COPR. Okay, so for us to see the efficiency of the refrigerator. The objective of a refrigerator is to remove heat QL from the refrigerator space. In order to achieve the objective, it requires a work input W net in. Thus, the COPR for a refrigerator is expressed as COPR equal to desired output minus by the required output QL over W net in. So W net in equal to QH or minus QL and also COPR, okay, coefficient of performance equation. Can also be replaced in a rate form. Okay, so you guys already know this one. Okay, so we have another example, example 5.2. A household refrigerator with a COP of 1.2 removes heat from the refrigerator space at a rate of 60 kJ per minute. Determine the electric power consumed by the refrigerator and the rate of heat transfer to the kitchen air. Okay, so this is the equation, the question, the answer. Here also I have another question for you. Please do it by yourself and refer to the answer provided in this slide. Okay. Alright. Now we have learned heat engine and then air conditioner. Okay. Oh no, not air conditioner. It is refrigerator. So now we want to learn about heat pump. Okay, heat pump. Another device that transfers heat from a low temperature medium to a high temperature is a heat pump. Refrigerator and heat pump operates on the same cycle but differ in their objective. So for a refrigerator, it is to maintain the refrigerated space at a low temperature by removing heat from it. But for heat pump, it is to maintain a heated space at a high temperature by absorbing heat from a low temperature source, such as well water or outside cold air during winter, and supplying this heat to the high temperature medium such as a house. So how about if we place an ordinary refrigerator near to the window of a house with its door open to the cold air outside during winter? So what if we do that? Okay, we'll place an ordinary fridge near to the window of a house. Okay, and now it is heavily raining or heavily snowing, so it is very cold outside. So what will happen? What will become? The refrigerator will try to cool the outside air by absorbing heat from the low temperature outside air and rejecting this heat into the house through the coils behind the refrigerator. So it is the mechanism of heat pump. So this is the mechanism of heat pump. So this is the equation for the performance efficiency of heat pump. COPHP, okay, it's the same with COPR. You can see by yourself, okay, or even read by yourself, okay, from Chengel Thermodynamics book. Okay. I have another example for you. Please do it by yourself and refer to the answer. Okay, now we move on to the second law of thermodynamics statement by closures. Yes, just now we learned the statement by Planck. Okay, so now it is from closures. It is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to a higher temperature body. It states that a refrigerator cannot operate unless its compressor is driven by an external power source such as an electric motor. This way, the net effect on the surroundings involves the consumption of some energy in the form of work in addition to the transfer of heat from a colder body to a warmer one. To date, no experiment has been conducted that contradicts to the second law, and this should be taken as a sufficient proof of its validity. Okay, this is the example. Okay, prove that the violation of the Kelvin Planck statement leads to the violation of a Clausius statement. Okay, so this is the example. You can read it by yourself. The Kelvin Planck and the closure statements are equivalent in their consequences, and either statement can be used as the expression of the second law of thermodynamics. Okay, last we will touch a little bit on Carnot cycle. So what is Carnot cycle? Heat engines are cyclic devices and that the working fluid of a heat engine return to its initial state at the end of each cycle. Okay, because it is cycle, okay? So it will return back to the initial state. So the net work is equal to the cycle efficiency. Can be maximized by using the process that require the least amount of work and deliver the most by using reversible process. Okay, the best known reversible cycle is the Carnot cycle, first proposed by a French engineer, Sadi Carnot, 1824. The theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine. The Carnot cycle is composed of four reversible processes, two isothermal process and two adiabatic process. It can be executed either in a closed or steady flow system. Okay. So this is the cycle of a Carnot, okay, Carnot cycle. I want you guys to read this from the slide and make sure you understand, okay, properly about this subtopic, okay, because in chapter 6 there are lots of calculation on Carnot cycle. Okay, so this is the example execution of the Carnot cycle in a closed system. TH constant, okay, 1 to 2, process 1 to 2, and then we have process 2 to 3. We don't have anything here. Okay, and then for Aya, the another another example, okay, process 3 to 4, energy sink at TL, and then from 4 to 1, the insulation happen. Okay, insulation at the outside of the piston. So reversible isothermal compression and reversible adiabatic compression. Carnot cycle PV diagram. Okay, you can see the PV diagram for the Carnot cycle, and as you already know and learn in chapter 3, I believe, okay, the area under the curve is equal to the moving boundary work, okay, WB. Okay, so in PV diagram, the area under the process curve represents the boundary work for quasi-equilibrium process. Okay, area under curve 1 to 3, work done by the gas during expansion part of the cycle. Area under Q 341, work done on the gas during the compression part of the cycle. Alright, so this is another diagram, okay, for T and S diagram of the Carnot cycle. Okay, and here you can see the diagram, or I mean how it works and it relates to the PV and TV diagram. Okay, so the reverse Carnot cycle, okay, the Carnot heat engine cycle is totally reversible cycle. Therefore, all the processes that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. Okay, so if it can reverse, it is the same with the refrigerator. Okay, the refrigerator process. So we call this as Carnot refrigeration cycle. In this case, the cycle remains the same except that the direction of any heat and work interaction are reversed. So we have heat in the amount of QL is absorbed, okay, from low temperature reservoir, and also heat in the amount of QH is rejected to a high temperature reservoir. Work input W net in is required to accomplish all. Okay, so this is an example of the Carnot heat engine. Okay, for any heat engine and for Carnot heat engine, the thermal efficiency is quite difficult. So you guys please be careful by in using this equation. Okay, so if the eta is lower, okay, is lower, then it become the irreversible heat engine. If it is the same, it become reversible heat engine. Okay, if it's larger, then it is impossible heat engine. Okay, so the Carnot heat engine for reversible cycle, the heat transfer by ratio QH over QL can be replaced by the absolute temperature ratio TH over TL. So that equation can be replaced to this equation. A conceptual experimental setup to determine the thermodynamic temperature on the Kelvin scale by measuring heat transfer QH and QL. Okay, this is another example for you guys to do. Please do it by yourself and refer to the answer given in this slide. Okay, so in chapter 6, okay, we have finished chapter 6. Okay, in chapter 6, we introduce the second law of thermodynamics and what is the definition of thermal energy reservoir, and we learn about the heat engine, okay, how it violates the Kelvin Planck statement, and then refrigerator and heat pump, the Carnot cycle, okay, the reverse Carnot cycle, and a little bit of the Carnot heat engine. So I will see you guys in the next video, chapter 7. Thank you so much.